Hello there and welcome back to the Science Sleepy Minds. Outside your window the night hangs like a soft velvet curtain. Crickets mumble, distant traffic sighs, and the air is still, at least to your senses. But beneath your pillow, your bones, and the very earth you're curled up on, the universe is doing something astonishing. It's wobbling. Right now. Like literally right now. Gravitational waves, tiny ripples in space-time, are passing through your body as you listen. They stretch and squeeze space itself. They are the cosmic echoes of cataclysms so violent, so massive, and so far away that you should absolutely not survive them if you were any closer. Luckily you're not. So, you just lie there, blissfully unaware that your atoms just moved. Just a little. Like a fraction of a proton little. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And hey, drop your location and local time in the comments, so I know where in space-time you're listening from. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You lie in bed, and somewhere a billion light years away, two black holes spiral toward their doom. As they orbit, they churn space-time like it's syrup, sending out waves, like ripples on a still pond. Only that pond is the fabric of reality. And those ripples, they pass through everything. You don't feel them. No one ever has with their own senses. Your nervous system isn't built to detect a billionth of a meter wiggle, but they're there. LIGO and Virgo and other observatories have proven it. Space-time is not a static grid. It's stretchy, squishy, jello-like. And those little wiggles aren't random. They carry information. They are, in a way, messages from the past. Distant, ancient, violent pasts. Imagine a giant rubber sheet. Our favourite physics classroom toy. Now drop a bowling ball on it. That's mass warping space. Toss another ball nearby. It rolls toward the first. Gravity. Now, bounce the balls together and watch the ripples. That's your gravitational wave. Now, scale the whole thing up until the balls are black holes with 30 times the mass of the sun, and you're kind of getting there. The first time we caught one was in 2015. You'll hear more about that soon. But right now, just imagine lying peacefully in bed while these ancient tidal shifts of space roll silently across you, stretching your feet and squishing your head, then reversing over and over again. But so slightly, you'd need a ruler the size of the solar system just to notice. It's poetic in a way. The most colossal events in the universe, the merging of collapsed stars, the cannibalism of black holes, don't announce themselves with fireworks. They come as whispers. And because these waves don't interact much with matter, they don't scatter like light does. They pass through galaxies, clouds, and chaos like a ghost through a wall. That means they reach us almost perfectly intact. No distortion, no redirection. They're clean, pure records of whatever spawned them. Like an untouched cassette tape recorded during the Big Bang. Historians still argue whether humanity's greatest scientific shift came with the telescope, the microscope, or the particle accelerator. But now, gravitational wave astronomy wants a seat at that table. It's letting us listen to the universe for the first time. And unlike traditional astronomy, which watches for photons, gravitational waves give us stories no light can tell. It's like realizing you've been watching a silent movie your whole life, and suddenly, boom, soundtrack. But it wasn't always this way. For most of human history, gravity seemed boring, predictable. An apple falls, Newton nods sagely, and everyone moves on. But then Einstein showed up, did a little math magic, and casually dropped general relativity. The idea that mass bends space-time, and gravity is just how objects move through that bent geometry. Oh, and by the way, Einstein added in 1916, if something really big moves fast enough, it'll send out ripples in space-time. But don't worry, no one will ever detect them, they're too small. Which is funny because the entire modern field of gravitational wave detection exists because people went, okay, but what if we tried? Einstein wasn't wrong per se. These waves are absurdly weak by the time they reach us. You could drop a bowling ball on your bed, and the resulting mattress ripple would be 1,000,000,000,000,000 times larger than a gravitational wave passing through your bedroom. And yet, we built machines to feel them. You probably wouldn't notice if the Earth jiggled slightly, right? Unless you're a cat during an earthquake. But these instruments, LIGO, Virgo, KAGRA, they do notice. They use light beams and mirrors so precisely positioned, it would make a Swiss watchmaker break into a cold sweat. They've confirmed that yes, the universe does ripple, frequently, violently. And from those ripples, we've started to understand things we couldn't see before, like hidden black hole populations, stellar graveyards, and possibly even the origins of heavy elements like gold and platinum. But more on that glittering surprise later. For now, just let it sink in. As you lie there under your blanket, the universe is not static. It's breathing. It's vibrating. It's echoing with every colossal collision, every cosmic catastrophe that's ever occurred, and you are in the splash zone. Fringe thinkers once claimed gravitational waves were a myth, or at best a mathematical curiosity. One notable physicist in the early 20th century called them mere artifacts of coordinate choices, which is physicists speak for math hallucinations. But today, the chirps are real, recorded, verified. Still, not everyone agrees on everything. Historians and theorists debate whether early gravitational wave theorists, like Joseph Weber in the 1960s, were brilliant visionaries or charming cranks. Weber even claimed detections decades before LIGO existed. His data was later debunked, but his obsession laid groundwork others would build on. So next time someone tells you nothing's happening, or that space is quiet, feel free to correct them gently, maybe even smugly. Because it's not silent, it's just whispering in a language we've only recently started to understand. And now, with your ears figuratively tuned, you're ready to follow those whispers to their source. Einstein sits hunched over his desk, probably regretting how much coffee he's had, trying to make the universe behave with pencil and paper. It's 1915, and he's just finished rewriting Gravity. Instead of forces tugging on objects, he's shown that mass warps spacetime itself, bending paths like a heavy suitcase on a memory foam mattress. Objects follow the curves, and boom, gravity. But then, as he keeps tinkering, something strange pops out of the equations. If massive objects move quickly, like orbiting stars, they should send ripples through space-time. Literal vibrations of reality. He hesitates. He's not sure he even believes it himself. In 1916, he cautiously publishes a paper describing these waves. But honestly, he thinks no one will ever see them. Not because they don't exist, but because they're just so absurdly subtle. Imagine two bowling balls colliding on a trampoline. Sure, you get ripples. Now imagine those bowling balls are thousands of times heavier than the sun, and the trampoline is all of space-time. The ripples stretch light years. But by the time they reach us, they'd move your body less than the width of a proton. No offense, but you're not going to feel that during your REM cycle. Still, Einstein's prediction hangs in the air like an unsolved riddle for decades. A few physicists bite, most shrug and move on. After all, there's a world war going on. Then another. Who has time for space-time wiggles when the world itself is doing plenty of that already? It isn't until the 1960s that someone dares to try detecting them for real. Enter Joseph Weber, a man who looked at Einstein's never gonna happen, and said, "Hold my oscilloscope." He builds massive aluminum cylinders, Weber bars, that in theory should resonate like tuning forks when a gravitational wave passes through. Spoiler, they don't. Or maybe they do. It's complicated. Weber claims he sees signals. Headlines explode. First detection. Except, no one else can replicate it. Other physicists build similar bars and get nothing but silence. To this day, historians still argue whether Weber was a visionary ahead of his time or just hearing things that weren't there. Some say he was too trusting of noisy data. Others call him the father of gravitational wave detection. Regardless, Weber's failure lights a fire. It proves that people want to find these waves. That's often how science works, actually. Someone fails loudly enough that others decide to fail better. Meanwhile, back in Einstein's corner, physicists start re-examining those original equations. Turns out, even Einstein had made some math mistakes along the way. He flip-flopped on whether gravitational waves were even real. Yes, the guy who invented them. In the 1930s, he submitted a paper arguing they didn't exist after all. Peer review slapped that down gently but firmly. He changed his mind again. It's a mess. A beautiful, chaotic, squishy mess of math and doubt. But by the late 20th century, things begin to crystallize. We understand that yes, gravitational waves are real. Yes, they carry energy. And yes, they should be out there. Somewhere. So scientists shift focus from trying to feel the ripples with bars of metal to watching them dance in beams of light. And this is where the real magic begins. Imagine you have two mirrors, miles apart with a laser bouncing between them in a vacuum. The light travels back and forth, perfectly aligned, like two kids swinging exactly in sync. Now, if space-time stretches just a little, the laser beams go ever so slightly out of sync. That tiny delay, that's your gravitational wave. That's the concept behind LIGO, the Laser Interferometer Gravitational Wave Observatory. It's the opposite of dramatic. It just waits for years, for decades. Two enormous L-shaped facilities, one in Louisiana and one in Washington state, each with arms 4 kilometers long, staring into the dark, hoping the universe decides to ring a bell. Meanwhile, Einstein rests comfortably in his grave, smugly assuming no one will ever catch his space-time fish. And then, in 2015, just shy of 100 years after his prediction, LIGO hears something. But we're getting ahead of ourselves. Back in the early 2000s, people are still skeptical. Gravitational waves are like ghosts. They're supposed to be out there, but nobody's gotten a proper haunting yet. The theory's sound, the math works, but space is big. Black holes are rare, and the signals we expect are faint, fleeting, and fragile. And yet, in every lab meeting, someone asks, what if today's the day? We haven't even touched on the deeper weirdness yet. Gravitational waves don't carry information the way light does. They are the information, a waveform travelling at the speed of a light that is not composed of particles but of motion itself. There's no graviton detection, not yet anyway. No camera can snap a picture of one. They're changes in geometry. Your very idea of distance and time is shifting even if you can't feel it. One odd fringe theory once proposed that gravitational waves could be used for faster-than-light communication, because they interact so weakly with matter. It was a fun sci-fi detour, quickly dismissed. But still, people dream. And all the while, hidden in the math of Einstein's field equations, gravitational waves remain. Unavoidable, uncaring, beautiful. So here you are, tucked under your covers, wrapped in blankets and Wi-Fi signals, and somewhere, out there, space-time stirs. The planets above continue their quiet spins. Neutron stars smash together in the void. Collapsing black holes throw tantrums in slow motion, bending the cosmos around them. And from each of those events, a wave spreads outward, not of sound, not of light, but of space itself. It moves through galaxies, through dust and plasma, through time, through you. And it all started with one man, one theory, and one stubborn idea that gravity isn't a force, it's the shape of everything. So next time you trip on a step or drop your phone, blame Einstein. He turned gravity from a simple downward tug into a multi-dimensional mindbender that makes you feel like your mattress is subtly participating in black hole physics. Don't worry, you're doing great. You're lying there, comfortably sinking into your mattress, and just under the threshold of your perception, space itself is doing yoga. It's stretching, compressing, stretching again. These aren't vibrations you can hear or feel, at least not in the traditional sense. but gravitational waves are passing through you like gentle tides that you'll never consciously notice. And here's where your intuition starts to break down, because you're used to waves being something that move through stuff. Ocean waves roll across the surface of the water, sound waves ripple through air, but gravitational waves? They're something else entirely. They are the change. They don't move through space. They move of space. They are spacetime's response to violence. So what actually happens when one passes through? Imagine you're floating in a spaceship, arms stretched out to the sides like a sleepy starfish. A gravitational wave moving through you would alternately stretch you in one direction, say, lengthwise, while squashing you in the other. Then it would reverse, back and forth, just a tiny, gentle squeeze and pull dance of geometry. But don't worry, it's not enough to pop your joints or ruin your posture. The amount of movement is comically small. If the wave comes from a black hole collision a billion light years away, it might change the length of your outstretched arms by a fraction of the width of a proton, not even enough to drop your snack. Still, it's happening, right now, as you listen. You live inside this stretchy space-time, and gravitational waves prove it's not some rigid stage where the cosmic play unfolds. It's part of the cast, a method actor constantly reacting to the energy and movement around it. Of course, this is where most people's brains do a little bazet, because it's not intuitive. It's one of those, sure, I get it, but also, what? Kinds of truths. Like how your GPS has to correct for the fact that time runs slower, closer to Earth's surface due to gravity. Yes, really, your Uber wouldn't find you if Einstein hadn't been right. The fact that space-time is bendy, that it's not just a backdrop but a character, was already a huge leap. But the idea that it can jiggle, that it can carry information via vibrations that require no medium, no sound, or no particles, that was enough to give even seasoned physicists pause. That's where gravitational waves become both elegant and horrifying, because they are not just an abstract prediction, they're real, and that means the universe is less like a machine and more like an instrument. And if it's an instrument, that means it can be played. And it is being played. Every time two neutron stars lock into a death spiral, every time black holes crash together, every time the structure of space is jolted by mass in motion, the universe sings, not in sound, but in space-time itself. The music of the spheres wasn't entirely wrong, it was just on a different wavelength, literally. And those wavelengths, they vary. High-frequency gravitational waves come from smaller, faster events, merging stellar mass black holes, supernovae, collapsing neutron stars. These are the sharp, chirpy plucks of the cosmic harp. Lower frequency waves, those come from massive, slow-moving systems, like supermassive black holes orbiting each other for millions of years. Their song is deeper, slower, more like the hum of a throat-singing galaxy choir. We can't hear those with current detectors on Earth, but we're building ears for them. LISA, the space-based observatory, is one such future listener. You'll hear more about that later. Spoiler, it involves lasers in space. Still, it's important to understand now. Gravitational waves aren't all one kind. They span a wide spectrum, and just like visible light only shows us part of the electromagnetic spectrum, the gravitational spectrum is vast. We've only just begun tuning into its higher frequencies, and we detect them not with ears, but with precision light, interferometry to be precise. We'll dive deep into how that works soon, but for now, know this. We're catching space-time's wiggles by watching how laser beams interfere with each other as the shape of space itself shifts. It's like trying to hear an earthquake by watching the shadows of dancing trees. Now back to your bedtime brain. You might be asking, if gravitational waves are so weak, why do we even care? Why bother hunting them down with instruments so sensitive they can detect a change smaller than a proton in 4 kilometers of vacuum? Because what they carry is priceless. Gravitational waves are immune to the things that scatter or absorb light. Dust, gas, magnetic fields, none of these get in the way. That means when a gravitational wave reaches us, it hasn't been warped or edited. It's the raw recording of some of the most extreme events the cosmos can cook up. Historians still argue whether the discovery of gravitational waves in 2015 was more important than the Higgs boson in 2012. The Higgs was the final puzzle piece of the Standard Model, but gravitational waves? They opened up an entirely new way of observing the universe, like going from looking through a window to stepping outside and feeling the wind. There's also the fun fact that you've got gravitational waves to thank for some of the drama in your daily life. For instance, two objects in orbit, say a pair of dense neutron stars, lose energy over time because they radiate it away as gravitational waves. That means they slowly spiral toward each other. It's like cosmic slow dancing with a ticking clock. In fact, in 1974, scientists Russell Hulse and Joseph Taylor discovered a pulsar in a binary orbit, and they noticed it was losing energy, exactly as predicted by gravitational wave theory. They couldn't detect the waves directly, but they could infer them. That discovery earned them the 1993 Nobel Prize. It was the first strong evidence that gravitational waves weren't just theoretical fluff. They had teeth, they had impact, and eventually they'd make their entrance for real. Now here's a quirky side note. In the 1970s, a handful of Soviet scientists proposed that extremely advanced alien civilizations might use gravitational waves for interstellar communication. Why? Because they're so hard to block. The idea was never taken too seriously, but hey, if you're going to eavesdrop on the galaxy, maybe you want to tune in to what Spacetime is murmuring. Who knows what's out there, whispering in the waves? So yes, gravitational waves are stretchy, squishy, and impossible to feel, but they are real, and they're redefining our understanding of the universe's most dramatic moments. Next time you wake up from a strange dream, remember, somewhere out there, a star may have just died, a black hole may have swallowed its twin, and Spacetime sent you a ripple while you snored through it. Charming, isn't it? You've just drifted off in your imaginary spaceship, coasting through that squishy, undulating ocean we call Spacetime, when suddenly, bam, something colossal crashes in the distance. Not just any something. We're talking two collapsed stars or black holes circling each other at half the speed of light, getting closer, tighter, more desperate with every orbit. And when they finally touch, the universe doesn't just blink, it rings. Picture the entire cosmos as one vast, incomprehensibly huge bell. When those black holes collide, they strike it so hard that space-time itself vibrates. The sound is silent, of course. You're in the vacuum of space, after all. But the ripple moves outward, a pure gravitational wave travelling at light speed, telling anyone who can hear it exactly what just happened. This is what we mean when we say the universe has its own bell towers, not tall spires with swinging metal clappers, but stellar mass monsters slamming together to send out the deepest, weirdest peals of all time. Now your instincts might ask, why only black holes? Aren't there other things out there that smash together? Sure, there are. But black holes are the universe's drama queens. They're dense, quiet, invisible. And when they collide, they do it in a way that makes space-time itself throw its hands up and say, okay, I need a moment. That moment, that's the wave we detect. And it's not just the collision, it's the inspiral, the slow-motion death waltz where they circle each other thousands of times, gradually radiating energy as gravitational waves. Their orbits shrink, they dance faster, and the waves get higher in pitch. This whole process can last millions of years, but the final few seconds, that's when the real symphony starts. Gravitational waves from these events are often described as chirps, low frequency at first, then rising in pitch and amplitude before suddenly cutting off. That cutoff, that's when the two bodies merge into one, and all hell, beautiful silent hell, breaks loose in space-time. The black hole merger that made history in 2015, GW150914 if you like license plates, was exactly this. Two black holes, 1.3 billion light-years away, collided, and the resulting ripple reached Earth. It hit the LIGO detectors like the faintest knock on a door made of light, and yet we caught it. And that's wild. Because that ripple had been travelling all that time. It had passed through star clusters, galaxies, gas clouds, cosmic voids. It hadn't slowed down. It hadn't faded. It had just kept going, an unbroken message from the past. Historians still argue whether the first moment of that wave's detection was fully appreciated in real time. Some say the data pinged in, and scientists weren't sure what they were looking at for a few days. Others insist the champagne was chilling in anticipation. Either way, when the wave was confirmed, the room erupted. Years of waiting, years of silence, and then a chirp. But let's take a step back. What exactly are these black holes doing to make space-time ring? It's not just the collision, it's the incredible acceleration of mass. Remember, it's not motion alone that produces gravitational waves, it's accelerating mass in a non-symmetric way. Two cars driving side by side won't do it. Two cars crashing into each other and spinning wildly might. But now imagine those cars are collapsed stars with the mass of 30 suns, and they're moving at nearly the speed of light. That's where the space-time rubber hits the road. And the beauty is, the wave they produce isn't random. It has structure, it has rhythm. It tells you about the size, mass, distance, and even the spin of the black holes involved. You can think of gravitational waves like a fingerprint left by cosmic events, except instead of ink on paper, it's space-time on reality. Here's a fun fringe tidbit. In the 1990s, a few speculative physicists proposed that entire alien civilizations might be wiped out by close-range gravitational wave events. The idea was that, theoretically, the waves could deposit enormous energy near the source, enough to fry nearby planets or destabilize stars. There's no strong evidence for it, yet, but it gives you a good excuse the next time you burn dinner. Sorry, love. Gravitational wave exposure. Back in the real, but still fantastically weird universe, not all cosmic bells ring equally. When neutron stars crash, they also send out waves, but shorter, higher-pitched ones. Less bass guitar, more distressed violin. And when supermassive black holes merge, that's the pipe organ, slow, thunderous, and currently out of our listening range. But don't worry, we're working on that. In the meantime, the black holes we can hear give us an intimate look at the universe's hidden side. You see, black holes don't emit light, they don't glow, they don't shout their presence. But when they crash into each other, they can't help but disturb the very thing that holds the cosmos together, space-time itself. And that makes them ideal musicians for this grand gravitational concert. In fact, some astrophysicists describe this field as multi-messenger astronomy. It's not just about seeing the sky anymore, it's about hearing it too. Like suddenly discovering your favourite movie has a soundtrack you never noticed before. It's also helping us map the population of black holes out there. LIGO and Virgo have revealed black hole pairs that are heavier than expected. Some of them seem to be spinning weirdly. Some are formed from previous mergers, a sort of cosmic second marriage. Each ring of the space-time bell adds to our knowledge. And here's another bizarre consequence. When two black holes merge, they often send the resulting bigger black hole shooting off through space. That's because the gravitational waves carry momentum, and if it's lopsided enough, the remnant black hole gets a kick. Imagine a cannon firing itself backward. Some of these black holes might be racing through galaxies at thousands of kilometers per second, invisible, but on the move. Try not to think about the fact that one could be aimed vaguely in our direction. You're trying to sleep. So tonight, as you lie in the quiet dark, remember, the universe is not silent. It's filled with the distant clangs of cosmic bells, set off by the most massive and mysterious objects we've ever imagined. And those bells don't just echo, they reshape the fabric of existence. You're floating in it. Always have been. You're stretched out, motionless, drifting into that soft blur between wakefulness and sleep, when far below your feet, beneath the floorboards, beneath the Earth's crust, beneath the comforting hum of your everyday existence, Something impossibly delicate stirs. No tectonic plate shifts, no train rumbles by. Yet somewhere, in a sealed chamber surrounded by vacuum, mirrors and lasers, the universe has whispered, and someone heard it. Welcome to the ballet of light and silence known as LIGO, the Laser Interferometer Gravitational Wave Observatory. A name as dry as toast, yet hiding a machine so sensitive it can detect a change in length 1,000 times smaller than a proton. Go ahead and say that out loud. A proton. One of the smallest things we know of, and LIGO can measure 1,000th of that. Why? Because gravitational waves don't roar. They tap, they nudge, they pass through everything without fanfare. So if you want to hear them, you need to shut up and listen. Really, really carefully. LIGO does this with lasers because of course it does. Lasers are light's version of a straight-A student. Perfect, coherent, predictable. And LIGO splits one into two beams, sending each down a 4-kilometer tunnel at right angles to each other. At the ends are mirrors, hanging, floating, gently isolated from everything else. The light bounces back and forth thousands of times in these long tunnels kept in near-perfect vacuum, and when the two beams are reunited, they interfere, like two voices humming the same note, sometimes in sync, sometimes just a hair off. If nothing's changed, the beams cancel each other perfectly. Flat line. Silence. But if a gravitational wave passes through, it ever so slightly stretches one arm of the L-shaped detector and squashes the other. The beams fall out of sync. A whisper becomes a detectable tremble. This is called interferometry. And yes, it's as difficult as it sounds. Even a truck driving 2 miles away can ruin a reading. So can a squirrel on the roof, or a gust of wind, or a very determined ant probably. That's why LIGO has 2 detectors, one in Hanford, Washington, and one in Livingston, Louisiana. If both pick up the same signal at nearly the same time, it's real. Even so, scientists spent years fine-tuning. For most of LIGO's early life, it heard nothing, just the rustle of Earth. Then came advanced LIGO, the upgraded, refined, laser-tuned version of the original. It powered on in 2015, and within days, chirp. But let's not skip ahead. Let's savour the absurd beauty of what these detectors do. To catch gravitational waves, LIGO must maintain mirror positions so steady that the total motion is less than 1/1000th of a meter. That's like keeping a mirror still while balancing it on a stick, on a floating platform during a hurricane, while someone's whispering quantum uncertainty in your ear. They use seismic isolation, active damping, pendulums within pendulums. Even thermal fluctuations in the atoms of the mirror coatings are considered. One physicist joked, "It's like trying to detect a shadow falling across a ruler from the moon." And yet, it works. There are detectors in other countries too. Virgo in Italy, KAGRA in Japan, built underground in solid rock using cryogenic mirrors to stay cool and stable. They all work together now, listening for the same space-time murmurs. When multiple detectors hear the same ripple, scientists can triangulate the source, even estimate its location on the sky. It's like spotting a lightning flash not with your eyes, but by how 3 microphones recorded its faintest thunder. The LIGO team has even tested their system with fake signals. Sneaky injections into the data to make sure the whole process, from detection to analysis to oh wow, is working smoothly. The scientists call it a blind injection. In 2010, they tested the team with a fake wave. It was an elaborate practical joke, right up until they realized the detection wasn't real. You'd think physicists would be annoyed, but most were thrilled. It meant the system worked. It could be fooled, and that was the point. Fringe enthusiasts have long speculated about gravitational wave espionage. The idea, you could hide transmissions or events inside a wave, undetectable by conventional sensors. There's zero evidence of this, of course, but it hasn't stopped the occasional imaginative theorist from writing papers with titles like Information in the Spacetime Tremor. Nerd poetry, basically. Meanwhile, LIGO quietly continues its vigil. You don't really notice that LIGO is running. It doesn't make headlines every day, but in its quiet way, it's completely transformed our view of the cosmos. Black holes used to be theoretical oddities. Now they're regular guests. Neutron stars used to be exotic. Now we know they smash together often enough to help fill your jewellery box with gold. Historians still argue whether LIGO will be seen, a century from now, as the 21st century's equivalent of Galileo's telescope. Maybe, maybe not. But it's already changed everything we know about invisible events, and it's still getting better. Every upgrade improves its reach. Doubling the distance means 8 times more volume, and that means more chances to catch the universe in the act. But the most poetic thing, LIGO doesn't just show us new places, it shows us new times. Because gravitational waves travel through the cosmos unimpeded, they carry pure, untouched records from billions of years ago. They are ancient, honest, not scattered like light, not absorbed, not distorted, just a perfect echo of violence, arriving late but intact. And you're here to witness it, or more accurately to nap through it, while machines whisper the truth into our science inbox. So the next time someone tells you lasers are boring, or that science has no magic left, just picture a pair of laser beams dancing in vacuum, measuring the wobble of reality itself, so you can dream a little deeper. You're just about to slip into that delicious weightless drift where your limbs disappear, and time gets fuzzy, when suddenly, chirp, not in your ears, not even in your head, but in the universe itself. It happened on September 14th, 2015. You weren't paying attention. Don't feel bad. Most people weren't. But the universe was, and it made a sound. Not a loud one. In fact, it wasn't even sound, really. It was a gravitational wave. The first one humanity ever confirmed. A ripple in space-time so subtle, so perfectly formed, and so far away that it had been travelling for 1.3 billion years before it reached us. And when it did, it passed right through your body like a ghost. You didn't feel it, of course, but 2 detectors did. LIGO's arms, those perfectly still laser-lit tunnels we talked about, twitched. Just a little. For a fraction of a second, they disagreed. And from that disagreement, scientists heard what they'd been chasing for decades. A tiny, rising chirp. That chirp came from 2 black holes, one about 36 times the mass of the Sun, the other around 29. They had been spiralling toward each other for millions of years, locked in a doomed, spinning embrace. When they finally collided, they became a single black hole, and in the process converted about 3 solar masses directly into gravitational wave energy. 3 suns, vaporized into space-time ripples. It's hard to explain just how much energy that is. For a few moments, that system outshone all the stars in the observable universe, in gravitational waves, not in light, not in radiation, in the very medium of existence. And then, silence. Historians still argue whether the scientific community truly grasped the scale of that first detection in the moment. Some compare it to the day Galileo turned his telescope to Jupiter's moons. Others say it was bigger. We'd not just seen something new, we'd listened in on the private lives of black holes. The event was named GW150914, short for Gravitational Wave 2015 September 14th. The name's a bit uninspired, but when you're dealing with ancient cosmic collisions, you can't always be poetic. Still, people cried. Literally. Scientists in control rooms hugged each other like they'd just been handed the keys to the universe. Because in a sense, they had. That chirp wasn't just a beep on a graph. It was confirmation that Einstein had been right once again, even after a century of doubt and debates. It was the proof that black holes can and do merge. That gravitational waves are real, not just theoretical phantoms in the equations. And it was beautiful. If you look up the waveform, yes, they graphed it. It's a gentle slope that rises into a tight curve and then cuts off sharply. That's the in-spiral, the black holes closing in, the merger, the moment of impact, and the ring down, the final vibration as the new black hole settles into its forever shape. Physicists sometimes call that final ring down a quasi-normal mode, which sounds like a setting on a washing machine, but in reality, it's the black hole's version of a dying bell tone. Even space-time needs a moment to catch its breath. After GW 150914, the floodgates opened. LIGO detected more chirps, each one a new story. Some were louder, some fainter, some from heavier systems, some from lighter. Each detection taught us something new. How black holes form, how they pair up, how fast they spin, and how far they've travelled to reach us. Before gravitational wave astronomy, black holes were like rumours at a party. Everyone talked about them, but no one had seen one dance. Now, we were getting live recordings of their greatest hits. One quirky side note, that first wave hit Earth at night, about 4:50 AM UTC. If you were sleeping in Europe or the east coast of the US, the wave passed right through your bed, and you never knew. Even today, people wonder what else might be slipping past our perception. That night, some folks had weird dreams. A few pets barked. Coincidence? Definitely. Probably. Maybe. There was a brief fringe discussion about whether humans might someday feel gravitational waves with the right training or technology. Biofeedback devices tuned to space-time tremors. GravSense. But honestly, unless you can grow lasers and vacuum tubes for eyeballs, your nervous system's not invited to that party. And yet, despite their subtlety, these waves are speaking volumes. From GW 150914, we learned that black holes don't always sit quietly at the centres of galaxies. Some of them roam, some pair up, some collide in isolation far from stars and light. One open debate still buzzing is how these black holes found each other. Were they born as a pair, massive stars orbiting, dying, collapsing in sync? Or did they meet later in a chaotic cosmic environment like a star cluster, attracted by gravity and destined to merge? The wave doesn't say. It doesn't give you the whole story, just the last chapter. You have to work backward from the final chirp to guess the rest. It's like showing up at a crime scene with only the sound of the victim's final footstep and trying to solve the mystery. But scientists love that kind of puzzle, and with each detection since GW 150914, we've sharpened our skills. We've gotten better at guessing the masses, the spins, the distances. We've even started using gravitational waves to measure how fast the universe is expanding. A job once reserved for supernovae and galaxies. The waves are turning into tools, and perhaps the strangest part. That first chirp, the one that confirmed Einstein, proved LIGO's worth, and launched a new era, was technically heard before LIGO's first official observing run had even begun. It was caught during engineering tests. The universe, it seems, couldn't wait. So now, as you sink into the pillow, remember, the universe does speak. It hums, it rings. And once, not so long ago, it chirped softly in the early hours of a September morning, and the world changed forever. You didn't hear it with your ears, but you're hearing it now. You're drifting comfortably now, wrapped in a heavy kind of stillness, like the hush that falls after a symphony's final note. But what if you could see that note? Not as a mark on a page or a spike on a waveform, but as a story. The complete narrative of a cosmic event etched in space-time itself. Because that's what gravitational waves are. Not just blips, not just chirps. They're messages, written in the language of curves and squiggles, carrying detailed autobiographies of the most extreme objects in the universe. So tonight let's sit with one wave a little longer, stretch it out, tilt it toward the light. Let's ask, what's in the shape of a gravitational wave? Let's start with the basics. Each wave that arrives on Earth carries a unique signature. The frequency tells us how fast the objects were orbiting before the collision. The amplitude reveals how massive they were and how far away. The waveform itself, the rise, the fall, the sudden cutoff, isn't just noise. It's an entire drama compressed into a few milliseconds. It's a little like holding a seashell up to your ear, only instead of ocean sounds you hear two stellar mass black holes orbiting each other 75 times per second. roughly 1.4 billion light-years away, spiraling closer, faster, tighter, until the singularity wins. Now, if that doesn't lull you to sleep, I don't know what will. The waveform starts low and slow, just a gentle ripple. That's the inspiral phase, where the two objects orbit calmly, radiating energy away. This part can last thousands of years, but we only see the very end. Then comes the crescendo, the merger, where the frequency and amplitude spike rapidly. The pitch rises, the wave tightens, and space-time briefly loses its cool. After the merger, the ring-down begins. That's the new black hole vibrating like a struck bell, settling into its final shape. These vibrations fade quickly, swallowed by the newly formed event horizon. Nothing more escapes. That's the sharp cutoff in the waveform. That's the moment the universe stops telling the story. But even that abrupt silence is valuable. From it, we learn about the new black hole's spin and mass. We can even check whether it conforms to predictions made by general relativity. So far, Einstein's still holding court, but scientists are watching closely, looking for any tiny discrepancies in the waveform that might suggest new physics, a crack in the curtain. There are even rumours, whispers really, of potential echoes in the ring-down phase. Tiny repeated bumps in the waveform that could indicate exotic physics at play. Wormholes, firewalls, quantum gravitational structures just outside the event horizon. Historians still argue whether we'll ever prove those echoes are real or just noise. Some claim to have seen hints, others roll their eyes. The data for now is too fuzzy, but oh, if they're right. Even more astonishing, scientists have begun to use parameter estimation algorithms to reverse engineer the entire event from the waveform. Think CSI, black hole. They plug the shape of the wave into models, and out pop the likely masses, spins and distances of the objects involved. It's like reading a novel backward and reconstructing the entire plot. And then there's spin. If the black holes were spinning, either aligned or at weird angles, the waveform twists in subtle ways. Misaligned spins cause precession, which introduces a kind of wiggle or modulation to the otherwise smooth chirp. Picture two dancers spinning while orbiting each other, but one's got a limp and the other keeps looking over their shoulder. It's messy, but it leaves a signature, and that signature helps us understand where these systems might have come from. If their spins are aligned, maybe they were born together, from a binary star system that aged gracefully into a pair of black holes. If their spins are all over the place, maybe they met in a chaotic star cluster, like two strangers in a dark alley colliding with dramatic consequences. There's even a whole category of waves called eccentric mergers. These involve black holes that didn't slowly spiral together in circular orbits, but instead came together suddenly on wildly elliptical paths. These leave bursts of high-frequency noise, a messier, more chaotic waveform, still decipherable, still telling a story. But less like a lullaby and more like freeform jazz. And then there are mass ratios. Not all mergers involve equal partners. Some waves reveal a lopsided duo, say a 30 solar mass black hole and a 5 solar mass black hole. The resulting waveform is subtly stretched, like a heartbeat with an arrhythmia. These mergers are harder to detect and model, but when they're caught, they provide insight into the gravitational wave spectrum's more obscure corners. Now for the real bedtime brain twist. If two black holes merge, and the result is just another black hole, how do we know we're not detecting the same one over and over? Here's the thing. Each waveform is unique. It can't be duplicated, not even close. The shape of the signal depends on a dozen variables: masses, spins, orbital dynamics, even the angle at which the wave reaches Earth. There's no such thing as a generic chirp. Fringe theorists have floated the idea that there could be template overlap with extreme black hole mergers, meaning two different events might produce nearly identical waves. But current detection methods account for this, and the odds are astronomically low, unless the universe is playing some elaborate prank. Spoiler, it might be. Some scientists have jokingly suggested that the same black holes are merging across multiple universes, and we're catching echoes from parallel realities. No evidence, of course. But it's comforting to know that even physicists like a good bedtime story. So what does all this mean for you, cozy under your blanket, eyelids heavy? It means the universe doesn't just make gravitational waves, it signs them. Every ripple is a letter, every waveform a love note or breakup letter between stars. And when we catch them, we read those messages, we decode them, we file them away like librarians of cosmic catastrophe. From a single chirp, we can reconstruct the entire dance, the partners, the tempo, the final bow. It's ridiculous, it's beautiful, it's real. So the next time you feel like the universe is distant, silent, cold, remember, it's been writing to you, constantly, with the gentle quiver of space-time itself. You just needed the right ears to hear it. You're deep now, nearly adrift, drifting not just through thought but through time itself. And fittingly so, because gravitational waves don't just travel across space, they carry you across time. Every ripple that passes through your body tonight is a direct message from an event that happened eons ago. Think about it. The first gravitational wave we detected in 2015 started its journey 1.3 billion years ago. That's before the dinosaurs, before flowers, before Earth even bothered with oxygen in its atmosphere. Back when the first multicellular organisms were just starting to wonder what all the fuss was about. And the wave has been moving ever since, at the speed of a light, through galaxy clusters, interstellar voids, cosmic filaments. It passed stars forming and dying. It rode alongside photons from the dawn of time. It crossed unimaginable distances, not stopped, not scattered, not even slowed. That's the beauty of gravitational waves. Unlike light, which can be absorbed, bent, or smeared by dust and gas, gravitational waves don't care what's in their path. A black hole? Cool. Pass right through. A neutron star? No problem. An entire galaxy? Barely worth noticing. They arrive pure. So when you detect one, you're not just hearing an event, you're time travelling. You're listening to something that happened before your species evolved kneecaps. It's the ultimate cosmic voicemail. And the signal isn't static. It holds the rhythm and structure of the moment it came from, like a fingerprint preserved in space-time. So when we catch a wave, we're eavesdropping on the exact second two black holes collided, so far away and so long ago that by the time the wave hits Earth, the light from that same event might never reach us. That's one of the weirdest parts. Some of these events are invisible in every other wavelength. They don't emit light. No X-rays, no gamma rays, nothing. If not for gravitational waves, they'd remain undetected forever, lurking in the shadows of time. Historians still argue whether this kind of non-electromagnetic astronomy represents a deeper truth about the universe, or just exposes how blind we were before. Either way, the message is clear. We've only just begun to listen. Gravitational waves are the universal medium. They carry more than energy. They carry information. In fact, they've already forced us to reimagine certain parts of cosmology. For instance, by measuring the distance to a source via its waveform and combining that with a redshift, if we can find a matching light source, we can calculate the Hubble constant, the rate at which the universe is expanding. That's right, we're now measuring cosmic expansion with black hole collisions. This method is called using standard sirens, a twist on standard candles like supernovae, and it might even help solve one of the biggest mysteries in astrophysics right now. Why different methods give different answers for the Hubble constant? Quirky tidbit? When the first gravitational wave detections came in, some physicists joked that we were finally picking up on God's Wi-Fi. Others insisted we were just tuning into space-time's natural background noise, like leaving a cosmic baby monitor on and occasionally hearing a black hole burp. Either way, these waves are giving us real-time access to the deep past, like flipping through a scrapbook of supernovae and neutron star smashes, but in audio format. And this leads to a wild thought. gravitational waves travel undisturbed through the entire observable universe. That means we could, in theory, detect events from the very edge of space-time, the most ancient sources imaginable, not just stars colliding, but the actual moment the universe began to expand, the Big Bang itself. More on that later. Oh yes, we're definitely going there. But for now, consider how far these waves travel, and how long, and what that means. Because here's something grounding. Gravitational waves don't just tell us about the past. They help us understand now. They're letting us test relativity in places where it should break, under extreme gravity, under insane velocities. And so far, general relativity is holding up like an overachieving honour student. But we keep looking, keep comparing. Every new wave could be the one that shows a tiny deviation, a hint that something's missing, something new, something quantum. Somewhere in those ancient waveforms might be a clue that bridges gravity and quantum mechanics. Or maybe not. But you won't know unless you keep listening. This is where gravitational wave astronomy differs from the rest. It's not just about capturing snapshots of cosmic events. It's about reading the entire timeline of what happened. You see the slow acceleration of black holes, their spiraling decay, the snap of their union, and their echo afterward. You get the whole arc. The beginning, middle, and end. Light-based astronomy? It's mostly glimpses. This is the full reel. And it works in reverse too. The better we understand gravitational wave sources, the more we can use them as cosmic clocks. We can trace their paths backward, estimate when they formed, guess what the universe looked like in that time and place. They become probes, not just of physics, but of history. And as more detectors join the network, India is building one, China might follow. The global system becomes more precise, like adding more ears to a symphony, so you can finally tell where the cello is coming from. Fringe theorists? Oh, they've had a field day with this one. Some claim we might detect gravitational waves from civilizations, not natural collisions. Artificial signals generated deliberately to span vast distances. The idea being, if you wanted to leave a message for someone millions of light years away, and you didn't care how long it took to arrive, gravitational waves are your safest bet. They last, they don't degrade. No evidence for that yet. But you can bet someone's working on the search algorithms. So tonight, as you sink deeper into the mattress, let this comfort you. The past is not lost. It's still rippling outward, still reaching you. And the fabric of space-time, for all its complexity, is kind enough to carry those ancient messages intact. You just have to lie still and listen. You're fully tucked in now, limbs warm, mind softening, thoughts floating like dandelion seeds. But there's one more thing you should know before you drift off completely. That peaceful, silent night sky you see above. Yeah, it's a lie. Not a malicious one, more like a polite omission. You see stars twinkling, a few planets shining, maybe even the glow of the Milky Way if you're lucky. But what you don't see is the constant, relentless violence of the cosmos. Stars collapsing, black holes devouring their partners, neutron stars crashing into each other like bowling balls made of nuclear fire. Space isn't still. It isn't quiet. It isn't resting. It's just that your eyes, and even your best telescopes, have been watching the wrong kind of drama. Because the universe is loud. Deafening, actually. You just haven't been listening in the right way. But gravitational waves, they're changing that. They've peeled back the curtain, revealing a version of the universe that's a little unhinged, if we're being honest. Underneath all the starlight and calm, space is having a full-on meltdown all the time. That quiet you thought you knew, it's saturated with ripples. And now that we've started listening, we're hearing just how busy the universe really is. Before gravitational wave detectors came online, we had a pretty limited understanding of black hole mergers. We thought they were rare, maybe a couple per galaxy per million years. Nothing you'd really put on your cosmic calendar. But now, LIGO and Virgo are detecting these events regularly, dozens of them. That's like assuming earthquakes only happen once a century, then turning on a seismograph and realizing they've been rumbling under your feet constantly. just too faint for you to feel. Historians still argue whether this proves that black holes are simply more common than we thought, or if our models of stellar evolution need a serious update. Either way, we were wrong, and it gets weirder. Some of these black hole mergers involve objects that shouldn't even exist according to previous theories. We're talking masses too large to come from a normal star, too small to be supermassive, right in the mass gap, a zone where black holes weren't supposed to form naturally. Yet here they are, flinging gravitational waves at us like cosmic pranksters saying, "Surprise!" And then there's the timing. Black holes aren't waiting around to merge. Some of these events are happening faster than expected, meaning some black holes may form and crash into each other in less than a few 100 million years. That's cosmic speed dating, and it's a red flag for our entire understanding of how stars live and die. Add to this the occasional oddball wave, a strangely tilted spin, a suspiciously high eccentricity, or a waveform that ends just a little too abruptly, and you start to realise the universe is not just noisy, it's messy, it's improvising. It's like discovering your quiet neighbour is actually leading a double life as a death metal drummer on the weekends. But instead of drums, it's black holes. And instead of weekends, it's all the time. You've probably heard the phrase silent universe. It's the romantic idea that in space, no one can hear you scream. Technically true, yes. No air, no sound. But it turns out the universe is screaming. It's just doing it through gravitational waves which we're only now learning to interpret. Fringe scientists, read the fun ones, have even proposed that the entire cosmos is vibrating all the time, at every frequency imaginable. A gravitational wave background, always there, always humming, a permanent soundtrack to the life and death of stars. This idea is being tested too. In fact, the North American Nanohertz Observatory for Gravitational Waves, NanoGrav for short, recently picked up hints of a low-frequency background rumble, not from individual events, but from the collective roar of countless black hole binaries across the universe. It's like hearing not just one bell ring, but the soft, endless peal of an entire cathedral choir of collisions. And this changes things, because now we know the universe isn't just screaming, it's always been screaming. We just finally found the right microphone. That background hum might be one of the oldest sounds in existence, and once we fully understand it, we might be able to tease apart its threads, to identify individual mergers, track their histories, maybe even spot entirely new classes of objects we've never imagined. It's like switching from reading a book by flashlight to turning on the overhead lights and discovering it's actually a library. But the best part? We've barely scratched the surface. LIGO sensitivity is improving, Virgo is upgrading, KAGRA is joining the network, and soon, space-based observatories like LISA will take us even further into frequencies we've never accessed. We'll start hearing the deep, slow bass notes, the kind that come from supermassive black holes in distant galaxies, merging after billions of years. And those are the real bass drops of the universe, the ones you feel in your chest, or, in this case, your geometry. Somewhere out there, two galaxies have already begun their slow-motion collision. Their central black holes, each millions of times the mass of the Sun, are spiralling toward each other. It will take eons, but eventually they will merge. And the gravitational wave that comes from that moment? You'll hear it. Or rather, you'll detect it. Maybe not with your ears, maybe not even in your lifetime, but it's on its way. The ripples are already en route, surging through the void with perfect calm. So tonight, as you lie beneath the illusion of a peaceful sky, know this: the quiet isn't real. It's just the absence of the right kind of listening. The universe has never been silent. It's just been speaking in a language we've only recently begun to understand. Your breaths are slow now, the kind of steady rhythm that makes even the air feel sleepy. And yet, above your head and far beyond your dreams, the universe is doing something spectacular, something almost poetic in its brutality. Two neutron stars, the densest objects this side of a black hole, are spiraling into each other in a dance that ends in glorious, physics-defying wreckage. Yes, it's time we talked about the 2017 event, the neutron star merger, the one that gave us gravitational waves and light, the one that taught us where gold comes from. Because, spoiler alert, it's not from treasure chests or alchemical furnaces, it's born in the death screams of neutron stars. The event was dubbed GW 170817, and it was the first time humanity detected both gravitational waves and electromagnetic signals from the same source, a double whammy. The kind of cosmic alignment that makes astronomers cry tears of joy and frantically call everyone they've ever met. It began, as usual, with a chirp. On August 17th, 2017, LIGO and Virgo picked up a gravitational wave that was different, softer, higher in frequency. It didn't match the usual signature of two black holes. This time, the objects were smaller, around 1.4 solar masses each, and as they spiraled together, the waveform was longer, more drawn out. It hinted at something denser than a star, but not quite a black hole. Neutron stars, the collapsed leftover cores of supernova, just 10 to 15 miles wide but more massive than the Sun. Think of a sugar cube of neutron star matter. It would weigh as much as a mountain. They're so dense that their atoms have collapsed into a soup of neutrons, packed together like commuters on the last train home. And when two of them collide, well, space sings, and this time, light shines. Historians still argue whether this was the most important astronomical event of the 21st century. Probably yes. Not only did the gravitational wave signal tell us about the collision, but, just 1.7 seconds later, NASA's Fermi Gamma Ray Space Telescope caught a short gamma ray burst in the same region of the sky. Gamma ray bursts are the universe's fireworks display, brief, blinding flashes of the highest energy light we know. And this one, it matched the gravitational wave. Two entirely different instruments, two entirely different forms of observation, picking up the same event nearly simultaneously. For the first time, we had multi-messenger astronomy in action. Then came the follow-up frenzy. Telescopes all over the world scrambled to the coordinates. Within hours, they spotted the fading afterglow in a galaxy 130 million light-years away, NGC 4993. The event even produced visible light, X-rays, ultraviolet, and radio waves. It was like the entire electromagnetic spectrum showed up to the party. And what a party it was. This kind of event is called a kilonova, a brief, brilliant explosion that occurs when neutron stars merge. For a couple of days, the debris glows with unbelievable heat. But here's the kicker. The explosion is rich in neutrons, and those neutrons allow rapid nucleosynthesis, the R process, to occur. Translation, it's a cosmic factory for heavy elements. That includes gold, and platinum, and uranium. Basically, all the bling in your jewelry box and the battery in your smoke detector were forged in a neutron star collision. Somewhere out there, two dead stars collided in a galaxy you've never heard of, and billions of years later, part of that mess ended up on your finger. You're wearing space wreckage. Elegantly, of course. And that's the kind of perspective gravitational waves are offering us. Not just, ooh, black holes, but here's how the universe makes stuff. Real, tangible stuff. The ingredients of Earth, the elements in our bones, the dust in your veins may well have originated in an ancient kilonova. Quirky tidbit. Before GW 170817, scientists weren't 100% sure what caused short gamma ray bursts. They suspected neutron star mergers, but they didn't know. This event sealed the deal. Gravitational waves were the missing proof. And the precision? Astounding! From the waveform alone, scientists could determine the masses of the neutron stars, their distance, and even some details about the matter involved. There was also a tiny, tantalizing hint of what happened after the merger. Did it collapse immediately into a black hole? Or did it form a hypermassive neutron star for a few moments? We're still not entirely sure. That's an ongoing debate. The signal tapered off before we could catch the final outcome with certainty. Some models suggest the merged object briefly resisted collapse, supported by thermal pressure and differential rotation, a temporary spinning monstrosity held together by physics equivalent of duct tape. Others think it caved in almost instantly. The jury's out. Either way, the implications are profound. This wasn't just a proof of concept, it was a gateway, a cosmic Rosetta Stone. It showed us that gravitational waves and light can work together, like different senses painting a fuller picture. You don't just hear the universe, you see it. You taste its elements in your bloodstream. And it raised new questions too. What other processes might produce both waves and light? Could some black hole mergers do it? What about exotic matter? What about strange stars? Hypothetical objects made of quark soup rather than neutrons? There's so much we still don't know, but one thing's certain. Since 2017 we've been on the hunt. Astronomers now scan the sky after every gravitational wave detection, hoping for a matching flash. Most of the time, nothing. Just dark, the usual black hole culprits. But once in a while, maybe, just maybe, we'll catch another killer nova in the act. So tonight, as you drift a little further into the abyss of sleep, think of those stars out there, dead, collapsed, invisible to the naked eye, quietly preparing their final pirouette. They'll crash, they'll explode, and the universe will ring like a crystal glass and shine like a chandelier of pure elemental gold. And somewhere, someday, one of those ripples will wash over you, unfelt, unheard, but very, very real. You're floating now, just a soft presence in the dark, when suddenly you feel it, not with your skin, not with your ears, but somewhere deeper. A tremble, not dramatic, just enough to remind you that somewhere out there reality just got stirred. Again. Only this time it came with light. You've already met the star of the 2017 Gravitational Wave Gala, GW 170817, the neutron star merger that lit up the sky in every possible wavelength. But what made that moment so spectacular wasn't just that we saw something, it's that we heard it too. The gravitational wave and the light wave arrived together, side by side, like perfectly choreographed dancers. And this was more than just good timing, it was scientific gold. You see, most of what we've learned about the universe has come from light. From Galileo's telescope to the Hubble Space Telescope, we've been watching the sky like silent moviegoers, trying to understand the plot based on facial expressions and explosions. But gravitational waves? They're audio, they're vibration, they're touch. They let us feel the universe's most private moments, not just when something glows, but when it moves. Especially when that motion is too violent, too buried, or too dark for light to escape. This is the essence of multi-messenger astronomy, the combined use of light and gravitational waves, and sometimes neutrinos, to get a full spectrum story of cosmic events. Imagine trying to understand a thunderstorm by watching it through a soundproof window. You can see the flashes, sure, but you have no idea how loud it is, how close it feels, how it rumbles in your chest. That's what gravitational waves give us, the thunder. And when you match it with the lightning, you get something more complete. So what exactly do we learn from each type of signal? Light tells us about the outer layers of events, the glow of gas, the radiation from high-energy particles, the lingering shimmer of radioactive decay. It gives us images, temperature, composition, colour, beauty. Gravitational waves, on the other hand, come from the core, the bones of the event, the final seconds before two stars or black holes collide. They carry information that no telescope can see. How fast things were spinning, how massive they were, how warped space-time became in those final furious orbits. Put them together, and you get context. You get a beginning and an end. GW 170817 was the best of both worlds. But it also showed us something extraordinary, that gravitational waves arrive at the same speed as light. Within 1.7 seconds, to be precise. That's not a big delay. not when you've travelled 130 million light years. Historians still argue whether that 1.7 second gap is just from the physics of the merger itself, like maybe the gamma ray burst had a slight delay in launching, or if it hints at something deeper, maybe gravitational waves do move at exactly the speed of light, maybe they don't. The fact that it was that close, though, helped scientists rule out a huge class of theories that predicted different speeds. Einstein wins again, and hundreds of alternative gravity theories got sent back to the drawing board. But beyond the speed of propagation, there was something else: direction. Gravitational wave detectors are great at detecting events, but not always great at pinpointing them. A single detector can tell you something happened. 2 detectors can give you a broad patch of sky. But 3? Now we're getting somewhere. Thanks to LIGO and Virgo working together, we could narrow the location of GW 1708-17 to a small enough patch that telescopes could jump into action. That kind of cross-team coordination had never been done at this scale before. Within hours, dozens of observatories were scanning that corner of the sky. And then, there it was, a fading point of light in NGC 4993, the smoking gun. Some observers described it as blue at first, then fading to red. That colour shift told us about the temperature and velocity of the material ejected during the collision. Hot, fast radioactive material that cooled and slowed over days, and as it cooled, it left clues. Spectra from the kilonova showed the fingerprints of heavy elements forming. Precious metals, yes, but also radioactive isotopes that would decay and glow long after the event. Without gravitational waves, we never would have found that glow. Without light, we wouldn't know what was glowing. And together, they taught us something new, that the death of neutron stars is not just an ending. It's a birth of elements, of insight, of an entirely new way of observing reality. There are ongoing efforts now to improve this combo approach. Projects like Zwicky Transient Facility and the upcoming Vera Rubin Observatory are being built with fast reaction times in mind, able to scan huge swaths of sky quickly after a gravitational wave alert, like cosmic paparazzi, ready to snap the first picture of the aftermath. And soon, we'll add neutrinos to the mix. These ghost-like particles produced in massive explosions can pass through entire planets without blinking. If we catch those two, we'll have gravitational waves, light, and neutrinos, a trifecta of truth. Fringe thinkers have even proposed a fourth messenger: dark matter. What if we could someday detect its subtle effects on space-time alongside the others? No evidence yet, but we didn't have gravitational wave data a decade ago either, so who knows? The future of astronomy is no longer about bigger telescopes alone. It's about building a network of ears, eyes, and strange particle-sensing devices, all watching and listening to the same events, in real time from every angle. And the result? A universe that's no longer mysterious in its silence, but symphonic in its complexity. So as you turn over in bed, blanket tucked to your chin, picture this. Out there, in the vast night beyond your walls, something has just happened. A collision, a burst, a whisper. Maybe it's light, maybe it's waves, maybe it's both. And right now, instruments all over Earth, beneath mountains, deep in labs, floating in space, are reaching out to catch it. Because when the cosmos speaks, it doesn't use just one voice anymore. It sings. The night deepens. You're somewhere between waking and dreaming now, balanced on the edge of your own little event horizon. But as your breathing slows and your limbs grow heavier, a question quietly rolls in with the dark. Where do these black holes meet? Like, where are all these collisions happening? Are there special places in the universe that are just cosmically romantic? You know, where black holes find each other, flirt through a few billion years of orbital prelude, and finally crash together in a blaze of space-time glory? As it turns out, yes. Some galaxies are like nightclubs for black holes, the kind of places where the gravitational drinks are strong, the stellar music's loud, and the dance floor is dense. These are the so-called black hole factories, environments where the chances of two black holes meeting and merging skyrocket. Dense stellar clusters, globular clusters, galactic cores, even the debris-rich centers of active galactic nuclei. These cosmic hotspots are where black holes can meet new partners, not because they're born together, but because gravity introduces them. And this is where we leave the calm choreography of binary star evolution and enter the chaotic improv of dynamical formation. In quiet, boring space, say, in a standard spiral galaxy like ours, binary black holes usually form from massive star pairs. They live together, die together, and collapse into black holes still orbiting one another. It's a slow burn, predictable, sweet even, a celestial till death do us part and beyond. But in a dense environment, it's a whole different story. Picture a crowded dance floor of compact stars and stellar remnants. Everything's moving. Close encounters happen constantly. Three-body interactions, no, not that kind, are common. One black hole might swoop in and steal a partner from another. It's pure gravitational drama, jealous orbits, ejected companions, sudden, unexpected mergers. This is dynamical formation in action, and it's messy, loud, and wonderfully efficient. And it's more than just theory. Some of the gravitational wave events detected so far seem to come from unusually massive black holes, too big to have formed in isolation. Some have spins that are oddly tilted or even anti-aligned, which suggests they didn't start life together. They met later, probably in one of these chaotic environments. Historians still argue whether most black hole mergers come from isolated binaries or dynamical pairings. The data's still murky. But if LIGO and Virgo keep detecting these oddball events, especially those with high eccentricity or strange spin dynamics, the dynamical camp might win out. But wait, it gets weirder. Let's say two black holes merge. Great. Now you've got a bigger one, but it's still sitting in the same environment, still surrounded by other black holes. So, what if it finds another partner? You're not wrong to picture a cosmic dating app, only instead of swipes there's gravitational capture, and the result? Hierarchical mergers. These are second-generation black holes, heavier, faster spinning, and often more chaotic than their predecessors. They're the black hole equivalents of people with really dramatic dating histories. LIGO has already picked up a few merger events that might be hierarchical. One in particular, known as GW 190521, featured a black hole in the so-called pair instability mass gap, a zone where, theoretically, black holes shouldn't form from normal stellar collapse. But it was there, and it was loud. One hypothesis? It was the child of a previous merger, a second-gen monster. This suggests that in the right places, globular clusters, nuclear star clusters, or dense accretion disks around active supermassive black holes might go on to merge multiple times, a whole lineage of increasingly massive, increasingly dramatic collapses. And if that's true, then the gravitational wave sky is more than just fireworks. It's an epic family drama stretching across eons. Some researchers are even exploring the idea that supermassive black holes might be built this way, slowly, through generation after generation of stellar mass black holes pairing, merging, and climbing the cosmic ladder. Fringe theory alert. There's a proposal that the LIGO-Virgo black holes aren't all astrophysical, that some of them might be primordial, formed just after the Big Bang, from density fluctuations in the early universe. These black holes would have no stellar origin, no parent star. Just a sudden collapse of matter moments after time began. They'd be ancient, silent, and if they exist, they could contribute to dark matter. No direct proof yet. But if gravitational waves can help distinguish the formation history of merging black holes, we might be able to test this idea. We're already building catalogues, plotting mass, spin, merger rates, location. We're turning black hole dating into forensic analysis. And it's not just about formation, it's about migration. In active galactic nuclei, the luminous centers of certain galaxies, there's so much gas and dust and radiation that stellar mass black holes can actually migrate through accretion disks, like pebbles sinking in molasses. They might find partners, spiral inward, and merge right there, creating waves and light. These environments could give us future multi-messenger signals. Some even speculate that gas in these regions can align spins before the merger. So if we detect a black hole merger with perfectly aligned spins, maybe it came from this hot, swirling, irradiated madness. And the truth is, we've only just begun mapping these gravitational matchmakers. So as you exhale, soft and slow, and your body sinks a little deeper into the mattress, imagine the sky above you, not as cold and sterile, but teeming with hidden dances, invisible orbits, tumbling collisions, second chances, third rounds, whole generations of collapsed stars trying, failing, and finally merging into something new. The universe doesn't just let black holes sit alone. It pulls them toward one another, gives them a stage, and lets them perform. And we, down here, listening with lasers and mirrors and vacuum tubes, are the audience. You're already in the front row. The room is quiet now. You're barely holding on to the edge of wakefulness, nestled somewhere between your own heartbeat and the soft breath of the dark. Let's slow everything down for a moment. Soften the sharp edges. Smooth out the ripples. Because before we go deeper into what's still to come, from giant space-based detectors to the echoes of the Big Bang itself, this is the perfect moment to look around and realize just how far we've come. You've gone from the faintest twitch of space-time to neutron star alchemy, to black holes that date, dance, and sometimes remarry. All of that, it's real. It's not science fiction. It's not hypothetical. It's happening, and it's being recorded by instruments quieter than your own bedroom right now. But for every loud chirp, every confident gravitational spike, there's something else humming just below the surface. A soft, endless background of almosts. Because not every gravitational wave is a clean solo. Some are part of a chorus. This is what scientists call the stochastic gravitational wave background, the gentle, persistent hum created by the superposition of countless unresolved gravitational wave sources. It's not one loud bang, it's not even 50, it's all of them. All the black hole mergers we missed, all the ones that happened before our detectors came online, even the ones too faint, too far, too numerous to separate. And it's not just black holes, it's cosmic strings, primordial fluctuations, collapsing stars in distant galaxies, a galactic whisper track that never ends. It's the soundtrack of a busy universe. Imagine standing in a crowded park, eyes closed. You don't hear one voice, you hear all of them. Laughter, footsteps, passing words, birds, none of them distinct, but together they make a kind of music. That's what the stochastic background is, and we're starting to hear it. In mid-2023, something extraordinary happened. Nanograve, the pulsar timing experiment we hinted at earlier, released results suggesting that we might be detecting this very background. Not from short, sharp chirps, but from long, slow wobbles in time itself. You see, nanograph doesn't use lasers or mirrors. It uses pulsars, rapidly spinning neutron stars that emit beams of radio waves like interstellar lighthouses. Some of these pulsars spin hundreds of times per second with perfect timing, like better than atomic clock timing. We monitor them, we listen, we watch the pulses arrive tick, tick, tick right on schedule, and if a gravitational wave passes between us and the pulsar, it warps space-time just enough to make the pulses arrive a teeny bit early or late. Not by much, maybe tens of nanoseconds, but across a network of pulsars, that subtle dance can reveal the low-frequency gravitational murmurings of the universe. The result? A possible first detection of the gravitational wave background. Not the big, flashy soloists, but the orchestra warming up. Historians still debate whether this counts as the beginning of a new era in gravitational wave astronomy. Some are cautious. The data isn't 100% conclusive. Others are already celebrating, arguing it's our first proof that supermassive black holes do in fact spiral toward one another in distant galaxies, shaping space-time like slow-motion hammers. Fringe theory time. Some researchers believe this background could carry imprints from before the formation of galaxies, clues about dark matter, cosmic inflation, even the shape of hidden dimensions. Imagine that. A gravitational fingerprint left not by stars but by the laws of physics themselves, back when the universe was a hot, dense fog of quantum uncertainty. We're not there yet, but we're looking. And while our Earth-based detectors aren't sensitive to these ultra-low frequencies, the kind with wavelengths longer than our solar system, projects like the European Pulsar Timing Array and Australia's PPTAA are teaming up with Nanograv. Together they form a kind of galactic scale detector, using space itself as the measuring stick. It's hard to grasp, but it means that even now, even as you lie here still and weightless, the sky above is a listening device. Your galaxy is part of a cosmic radar system, eavesdropping on the gravitational gossip of the early universe. And when LISA launches in the 2030s, it'll fill in yet another part of the spectrum. LISA will float in space, millions of kilometers from Earth, catching gravitational waves in a range we've never touched before. The deep, slow breathing of the cosmos, the marriages of supermassive black holes, the whispers from extreme physics. We're building an observatory that listens not just to explosions, but to histories. But that's a journey for another section. Right now you're here, suspended in this moment, wrapped in the soft hush of starlight and silence. And yet, even now, gravitational waves are passing through you. Probably not one, probably dozens, tiny, overlapping, indistinguishable, from collisions millions of light years away, from galaxies you'll never visit, from times before your ancestors were even a thought. And just as those waves move through you, something even softer follows: sleep. So let's wind it down for a moment. Let's quiet the machinery, put the black holes back in their distant, invisible orbits. Let the neutron stars stop colliding. Let the lasers take a breath. For a few heartbeats, let's let the universe hum. Let its rhythm settle over you, soft and wide and impossibly ancient. Imagine it not as noise, but as a lullaby older than time itself. Every wave a cradle, every ripple a breath. You're floating in space-time. It doesn't pull or push. It simply moves, gently, eternally, as it always has, as it always will. So rest now. You're safe. The universe can keep whispering its secrets. You'll be here to listen in the morning. The hum never really stops. Even as you sink deeper, even as the last conscious thoughts unravel like threads in warm water, the universe keeps its quiet background rhythm going. A vibration so subtle you wouldn't notice it if you had 1,000 years to try, but it's there. It's always been there. This is the gravitational wave background, a cosmic lullaby composed not by one event, but by all of them. It's not the sharp, chirping crash of two black holes colliding. It's the constant, overlapping murmur of billions of massive objects orbiting, wobbling, spiraling, dying, all at once. Somewhere out there, galaxies are merging. Inside them, supermassive black holes, each the size of millions or even billions of suns, are locked in enormous, swirling dances that last millions of years. They're not crashing yet, just circling, tugging at each other, whispering across space-time, and those whispers build up, one by one, over centuries, over eons, until the whole cosmos is wrapped in a low, endless thrum, too faint to feel, too long to hear, but unmistakably real. Scientists call this the galactic gravitational wave background. It's like standing in a crowded room full of murmuring voices. You can't pick out one sentence, one speaker, but the air buzzes with conversation. Space does the same. We can't detect this background with LIGO or Virgo. Their arms are too short, their range too high-pitched. What we need for this is something much grander, a cosmic scale detector. And we've already started building one. Not with steel, not with mirrors, but with pulsars. These little stellar remnants, rapidly spinning neutron stars, are scattered across the Milky Way. They flash beams of radio waves as they spin, like tiny metronomes in deep space. And when those pulses arrive just a bit early, or a bit late, That's a sign that something between us and the pulsar has shifted. A gravitational wave has passed through. This is the idea behind pulsar timing arrays. We don't just monitor one pulsar, we monitor dozens, all across the sky. When a low-frequency gravitational wave rolls by, one from a pair of supermassive black holes, for example, it stretches space in one direction and squishes it in another. That tiny distortion changes how long the pulsar's tick takes to reach Earth. So we map those ticks, we cross-check them, we wait. And eventually a pattern emerges. In 2023, the North American Nanohertz Observatory for Gravitational Waves, NanoGrav, made headlines by publishing strong evidence that we're starting to hear this background hum. They didn't catch one wave. They caught the hint of thousands, all overlapping, all ancient, all anonymous. Historians still argue whether this counts as a full detection, but the signal matches predictions. It behaves the way we expect a background of supermassive black hole binaries to behave. It may not be a full song yet, but the first notes are unmistakable. And just think about that. Right now, the entire Milky Way is being used as a gravitational wave antenna. Every pulsar is a sensor. Every bit of radio timing is a clue. We're using stars light years apart as endpoints in an experiment that spans galactic distances. Not a lab bench, not a telescope dome, but space itself. This hum is also a kind of ledger. It keeps the receipts of black hole mergers we'll never see. Ones that happened long before our species stood up. Ones that happened too far away, or too slowly, to ever send a visible chirp. But they left behind their fingerprints, subtle, tangled, encoded into the vibrations of space-time. And it's not just black holes. Some scientists think this background could include other contributors, hypothetical cosmic strings, leftovers from the early universe, or phase transitions from when the universe cooled in its first fractions of a second. Even primordial black holes, if they exist, could be in there, whispering from the first seconds of time. But even if it's just supermassive binaries, that's already mind-blowing. These aren't black holes the size of the sun. These are millions or billions of solar masses. They're at the centers of galaxies, huge, old, and terrifyingly calm. They take forever to merge, and yet, even from those slow-motion spirals, they send out waves. Deep waves, long waves, ones that take years to oscillate, not milliseconds, years. LIGO hears the scream, pulsar timing arrays hear the breath, and in between them, there's a gap, a sweet spot of mid-range frequencies. That's where LISA, the future space-based gravitational wave detector, will live. LISA will catch the middle tones, the ones too deep for Earth-based detectors, but too fast for pulsar timing arrays. We'll talk about LISA soon, but for now, picture this. The future of gravitational wave astronomy isn't just about bigger detectors, it's about a network, high, low, and in between, from the fastest chirps to the slowest rumbles, from stellar black holes to galactic giants. We're building an orchestra of instruments to hear the full cosmic symphony. Fringe thinkers like to joke that one day, the gravitational wave background will become our version of cosmic white noise, that you'll sleep not to rainfall or ocean sounds, but to filtered space-time vibrations, smoothed and sonified into a lullaby. Honestly, not the worst idea, but there's more than comfort in this hum. There's data, there's history, there are answers we haven't even thought to ask yet. And every new frequency range we open adds a new voice to the choir. So tonight, as your breath slows and the last tension leaves your body, imagine the air around you, not empty, but gently vibrating, not loud, not sharp, just constant, like a sea so vast and deep that the surface never stirs, but the currents below move with the rhythm of 1 billion unseen tides. You're floating in those tides. Let them carry you. Let the background hum wrap around you, deep and soft and infinitely old. The universe isn't just singing solos, it's humming a harmony that never ends. You're all but weightless now, draped across the fabric of space and time like a leaf on a pond. Every breath a ripple, every heartbeat a quiet echo. And still, even now, space-time itself is moving beneath you, just a little, not enough to notice, but enough that someone, somewhere, with the right instruments and the patience of stars can notice. Let's talk about those people. And more importantly, let's talk about the instruments they use that are so subtle, so clever, they make laser interferometers look downright flashy. Welcome to the world of pulsar timing arrays, and the absurd, beautiful idea that we can turn neutron stars into cosmic clocks. Picture a neutron star, a city-sized remnant of a supernova, weighing more than our sun and spinning hundreds of times per second. These objects are leftovers, survivors, the ghosts of once proud stars now compacted so tightly that even atoms have given up and collapsed into a sea of neutrons. But what makes millisecond pulsars so magical is their consistency. They spin and send out radio pulses with such perfect regularity that they rival atomic clocks. Seriously, they are some of the most accurate natural timekeepers in existence. Tick, tick, tick. Now imagine you're a scientist monitoring dozens of these pulsars spread out across the galaxy. Every pulse from every one of them arrives on Earth with near perfect precision. Unless something gets in the way. Or, more specifically, unless space-time itself gets wobbly. When a gravitational wave passes between Earth and a pulsar, it stretches or compresses the space in between just a little. That changes how long it takes the pulses to reach us. Maybe they arrive a few nanoseconds early. Maybe they're late. Maybe just by a whisper. But if you track enough pulsars, and enough of these whispers, a pattern starts to emerge. That pattern is the signature of a gravitational wave. Not a quick one, not a chirp. These are slow, low-frequency waves, ones with wavelengths measured in light years. You don't hear them in seconds. You hear them in decades. It's a whole different kind of listening. Historians still argue whether the creators of these early pulsar timing experiments, like Ron Hellings and George Downes in the 1980s, fully understood what kind of gravitational orchestra they were tuning into. But by 2005, efforts had coalesced into real collaborations. Nanograv in North America, the European Pulsar Timing Array, EPTA, and the Parkes Pulsar Timing Array, PPTA, in Australia. Together, they've become the International Pulsar Timing Array, or IPTA, a worldwide effort to turn the galaxy into a gravitational wave detector the size of the galaxy. And in 2023, something extraordinary happened. All the teams released data hinting at a shared signal, a common spectrum process, a soft, persistent, low-frequency hum in the timing residuals of dozens of millisecond pulsars. Not random, not noise, but coherent. A sign that gravitational waves from supermassive black hole binaries are finally brushing their long fingers across our galactic clock faces. Imagine that. Two galaxies merge. Their central black holes, each millions of times heavier than our sun, begin to orbit each other, slowly, majestically. With each orbit, they send out gravitational waves, huge, slow waves, wavelengths longer than star systems, frequencies that oscillate once every year. We can't detect that with lasers, but pulsars can. The idea is wild. We're watching clocks 1,000 light years away tick slightly differently because of a pair of black holes circling each other hundreds of millions of light years away. That's how still space is. That's how precise these stars are. That's how elegant this method is, and it gets even stranger. Because these timing variations aren't just local, they're correlated. If a gravitational wave passes through the galaxy, it stretches space in one direction and compresses it in another. So some pulsars' ticks arrive early, others arrive late. The exact pattern of timing shifts forms a map, a distinctive shape known as the Hellings-Downs curve. It's like watching the ripples of a pond and tracking how the waves move different leaves. In the 2023 data, the teams didn't just see noise, they saw the curve. It's not perfect yet. This is the soft opening of the show, but all signs point to a real, persistent signal. And if that signal gets stronger, we'll finally start to hear the slow-motion dance of galaxy-core black holes. Fringe theorists are already licking their pencils, dreaming up alternate explanations. Maybe it's cosmic strings. Maybe it's a relic from the early universe. Maybe, just maybe, it's something entirely unknown, a new form of gravitational radiation, or an interaction with dark matter that only reveals itself on galactic scales. But the simplest explanation is this: the universe is humming, and pulsars are the microphones. That's why these star corpses spinning alone in the dark matter so much. They're not just remnants, they're tools. Precision sensors scattered across the galaxy, ticking away in radio frequencies, waiting patiently for space-time to quiver. And that patience is paying off. Already scientists are imagining the next steps: more pulsars, better timing, longer data sets, improved sensitivity. If we can catch these low-frequency waves more clearly, we'll start tracing not just one binary but hundreds, maybe even entire populations of black holes across the observable universe. It will become a form of gravitational cartography. We'll map not stars, not galaxies, but mass in motion. Invisible dance partners, spiraling in slow, silent circles for millions of years. Finally noticed because they made one radio pulse arrive 10 nanoseconds too late. So as your body sinks into sleep, remember, time itself is your ally here. The slow waves, the long game, the quiet watches of the sky. We're not just listening for dramatic events anymore. We're attuning ourselves to the persistent breath of the cosmos, the long exhale of gravity at rest and gravity in motion. Somewhere out there, a pulsar just ticked, right on time, and somewhere else its next tick will be just slightly off because space-time in all its elegance just shifted by a whisper. You're almost fully gone now, draped in the quiet, floating along on this invisible river of time, letting the universe rock you gently with forces older than your ancestors and larger than your imagination. But just when you think the cosmos might settle down, it clears its throat and says, "Oh, we're just getting started." Because Earthbound detectors, LIGO, Virgo, KAGRA, have been extraordinary, but they're also limited. Gravity is generous with its waves, but Earth is inconvenient. There's seismic noise, human activity, even the weather. Vibrations from cars, from wind, from that squirrel having an existential crisis on the observatory roof. There's only so much quiet we can create on this noisy little planet. So what do we do when Earth gets too loud? We leave it. Introducing LISA, the Laser Interferometer Space Antenna, NASA and ESA's co-parented gravity-sensing baby, due to launch in the mid-2030s, floating in space, sunbathing in a perfectly stable orbit, far away from earthquakes, buses, and squirrels. LISA is a gravitational wave observatory, unlike anything that's ever existed. While LIGO has arms 4 kilometers long, LISA's arms will be 2.5 million kilometers long. That's not a typo. That's millions. In space, between spacecraft, 3 satellites will fly in an equilateral triangle trailing Earth in its orbit around the Sun. They'll exchange laser beams across vast distances, tracking minute changes in their separation. If space-time warps, just a little, those laser signals will pick it up. This allows LISA to detect lower frequency waves than Earth-based observatories can. Think of it like shifting from a flute to a bass drum. Earth detectors catch quick, high-pitched chirps. LISA listens for the long, slow groans of massive black holes merging and the constant murmurs of tightly orbiting white dwarf binaries. So why do we need LISA? Because there's a whole universe of gravitational waves we're not hearing. Right now we're missing the middle of the gravitational wave spectrum. Those long, slow waves from supermassive black holes, the kind that sit at the centres of galaxies and weigh millions, even billions, of times more than our Sun. These behemoths merge when galaxies collide, but their gravitational waves are too long and slow for LIGO or Virgo, and too fast for pulsar timing arrays. They live in the awkward middle range, LISA's sweet spot. and once Lisa's online, we'll finally start catching those monster mergers. Imagine two galaxies spiraling into each other over billions of years. Each has a black hole at its core. Those black holes eventually find each other. They orbit for millions of years, and then, finally, after untold eons, they merge. The resulting gravitational wave is a deep, slow, sustained crescendo that Lisa will hear long before the final smash. That's another advantage of LISA, early warning. Because these signals evolve slowly, Lisa could detect them years in advance. We'll watch black hole binaries approach their final plunge. We'll know when they're about to merge. Astronomers will have time to point every telescope on Earth toward the sky, ready for a potential light show. It'll be like preparing for a cosmic eclipse, except the eclipse is two black holes eating each other. Historians still argue whether this will be the greatest leap in gravitational astronomy since LIGO's first detection. Most agree, yes, it's not just a next step, it's a new class of observatory. Earth is a pond, Lisa is the ocean, and it won't be alone. There are other proposed space-based detectors in development, the Chinese Taiji mission, the Japanese DeSigo, all aiming to open up this middle frequency range, because every new band we access tells us something different. There's even speculation about turning the moon into a gravitational wave detector, using laser stations on its surface to build kilometre-scale interferometers in a noise-free vacuum. That idea is still firmly in the sci-fi category, but give it time. Fringe theorists are, as usual, already ahead of us. Some proposed space-based detectors could catch non-Einsteinian waves, ripples that don't follow general relativity. Others suggest Lisa could detect cosmic strings, relics from the early universe, snapping like rubber bands and sending out enormous gravitational wave pulses. Still others dream bigger. Could space-based detectors pick up gravitational waves from extra dimensions? From brain collisions in multiverse models? Could they record the first moments of the Big Bang, fossilized in the longest wavelengths imaginable? Maybe, maybe not. But they'll certainly catch the chaotic heartbeat of the universe in a new register. And Lisa's sensitivity isn't limited to cataclysmic events. It will also detect persistent orbiting systems, white dwarf binaries circling each other endlessly, emitting steady gravitational wave signals, thousands of them. A whole new kind of astronomy. Instead of catching events, we'll study gravitational objects, steady, predictable, enduring. It's like shifting from watching fireworks to studying stars. And here's a fun twist. Some of the systems Lisa will detect have already been identified by light-based telescopes. We know they're out there, we just haven't felt them yet. But when we finally do, it'll be like confirming an echo you always suspected was real. Lisa's even expected to see some of the same events as LIGO and Virgo, but earlier, when they're still in the low-frequency phase. That means a merger might first be heard by Lisa as a long, low whine, and then, weeks or months later, picked up by LIGO as a sudden chirp. Dual detection, full coverage, layered data, it's gravitational surround sound. So as you lie there, letting your own breath slow and your body melt into the mattress, think about those spacecraft, quietly gliding through space, locked in perfect formation. Laser beams stretching millions of kilometers through silence, waiting, listening, not for light, not for sound, but for the motion of the universe itself. The future of gravitational wave astronomy is silent, spacious, and absolutely colossal. It's not limited by our planet, it's only limited by our ambition and maybe our launch budget. But once Lisa rises, the whispers will become words, the echoes will become music, and you'll already know the tune. You're suspended now in that perfect weightless hush, mind wide open, limbs long forgotten. But just when you think the universe has shown you all its cards, it leans in and whispers, "What if we've been wrong?" Because for all our equations, our carefully tuned detectors, and our smug confidence in Einstein's genius, there's one thing we know for sure: every theory breaks eventually. and gravitational waves might just be the scalpel to find the seams in our most sacred physics. You see, up until now, everything we've talked about, the black hole mergers, the neutron-star collisions, the cosmic hum, it's all been described beautifully by general relativity, Einstein's theory, his crowning achievement, the one that turns gravity into geometry, the one that predicted gravitational waves in the first place. But it's also a theory that refuses to play nicely with quantum mechanics, and therein lies the crack. For decades, physicists have struggled to reconcile these two towering frameworks. On one hand, relativity describes gravity and the large-scale structure of the universe. On the other, quantum mechanics describes the small particles, forces, the jittery chaos of atoms, but together, like oil and vinegar, beautiful on their own, infuriating when mixed. So now, scientists are asking a wild but honest question. Could gravitational waves help us catch relativity slipping up? It's not a hit piece on Einstein. It's more like trying to hear the tiny imperfections in a symphony that's played flawlessly for over a century. And what better place to listen than in the deepest ripples of space-time? Let's break it down. Gravitational waves offer a testing ground unlike anything else in physics. They're generated in the most extreme conditions, speeds approaching light, gravitational fields strong enough to bend time into spaghetti, objects that literally erase themselves from view. If general relativity is ever going to crack, it'll crack there. Scientists are already watching. Every time a gravitational wave passes through LIGO or Virgo, they compare it not just to Einstein's predictions, but to alternatives. Do the waves travel at the speed of light? Do they stretch and compress in the right ratio? Do the polarizations match? Are there unexpected phase shifts? So far, general relativity keeps passing the test, but it's early, the sample size is still small, and there's an edge of anticipation in the air, because the tiniest deviation from expected behavior could reveal new physics, something beyond relativity, a window into the long-sought theory of quantum gravity. There are even specific things we're looking for, like graviton mass. In general relativity, the hypothetical graviton, the particle version of gravity, is massless. But what if it isn't? A tiny mass would cause gravitational waves to disperse, like light through a prism. The lower frequencies would travel slower. We haven't seen that yet, but we're watching. Extra polarizations. General relativity predicts only 2 polarization states for gravitational waves. Some modified gravity theories, like scalar tensor models, predict more. If we ever catch a wave with extra wiggle directions, game over for standard GR. Lorentz violations. What if spacetime isn't perfectly smooth? What if there's a graininess to it, a quantum foam beneath the fabric? That might cause tiny violations in Lorentz invariance, the bedrock principle that says physics looks the same no matter how fast you're moving. Gravitational waves might expose these effects over cosmic distances. Echoes. Remember those post-merger ringdowns we talked about? The way a black hole settles down after a collision? Some fringe theories suggest there could be faint echoes in that phase, reflections from just outside the event horizon, hinting at exotic physics like wormholes or firewalls. Nothing confirmed yet, but the data is being combed with surgical precision. Historians still argue whether gravitational wave astronomy will give us a clean break from relativity, or just more confirmation. It's hard to tell. But this is the first time we've had a laboratory in the strong gravity regime. Not just math, not just simulations, real data from real events. Fringe thinkers, bless them, have gone even further. They propose that some black hole mergers could involve non-standard compact objects, like boson stars made of hypothetical particles that don't behave like matter as we know it, or gravastars, hypothetical alternatives to black holes with no singularity inside. Some of these would produce gravitational wave signals almost identical to black holes until the very last moment. A different ringdown, a missing echo, a strange spin-down behavior. That's where the smoking gun might be hiding. Others argue that dark energy, the mysterious force accelerating the expansion of the universe, might leave subtle signatures in gravitational waves. Maybe it affects how they propagate. Maybe it subtly warps their frequency spectrum over billions of years. These ideas are speculative, yes. But speculation is where the fun starts. The instruments are here, the signals are arriving, and every waveform brings with it a new test. Even the speed of gravitational waves has become a probe of new physics. That 1.7 second delay between GW 170817 and its gamma-ray burst, it ruled out entire families of modified gravity theories. Some models couldn't explain both signals arriving so close together unless they were wrong, and just like that, poof, hundreds of theoretical papers invalidated by a single chirp. That's the kind of quiet ruthlessness science is built on. Elegant, merciless. And so now each detection isn't just an observation, it's an experiment, a courtroom trial, a chance to cross-examine general relativity under pressure. So far it holds up. But the cosmos is vast, the collisions keep coming, and the math, for all its beauty, might one day flinch. As you drift now into the deepest part of rest, know this. We are not just listening to the universe, we are interrogating it. And gravitational waves? They may yet be the question that cracks the answer wide open. You're deep now, drifting in the gentle black where even thought comes in slow waves. But just before sleep fully closes in, the universe has one more mystery to murmur in your ear. A quiet little phrase that sounds innocent at first, but unravels into the biggest puzzle in all of physics. Dark matter. You've heard the name, sure. Maybe whispered in documentaries. Maybe tossed into articles like seasoning. The universe is made of dark matter and dark energy, they say, like it's common knowledge. But here's the not-so-common truth. We don't know what it is. We don't know how it works. We only know it's there, like a ghost that doesn't interact with anything but still throws furniture around. And gravitational waves? They might just be the first method that lets us see its fingerprints. Let's start with what we know. When we look at galaxies, their stars move in ways that don't make sense. They spin too fast. Gravity alone, from all the visible matter, can't explain it. So we assume there's something else, invisible mass, exerting gravitational pull. A scaffolding made of something we can't touch. That's dark matter. It doesn't emit light, doesn't absorb it, doesn't scatter or reflect it. We've tried detecting it with particle accelerators, deep underground detectors, and even orbiting telescopes. Still nothing. But now, thanks to gravitational wave astronomy, we have a new tool. Because while dark matter may not interact with light, it most definitely interacts with gravity. So what could gravitational waves tell us? Plenty. For starters, the way gravitational waves travel can reveal a lot about the medium they move through. If space is filled with dark matter, clumps of it, halos, dense clouds, then as gravitational waves pass through these regions, we might detect tiny distortions, slower propagation, subtle phase shifts, frequency-dependent dispersion, the tiniest little fingerprints. Historians still argue whether such effects are measurable with today's detectors. Probably not yet. But with LISA and next-gen observatories, we might be able to see the gravitational lensing of gravitational waves, how their paths bend slightly as they pass near dense pockets of dark matter. Not light bending, space-time bending. Even more intriguing? Some physicists suspect that primordial black holes, those mysterious entities that could have formed right after the Big Bang, might be dark matter, or at least a part of it. And guess what? We might have already detected some. A few LIGO and Virgo events involve black holes that are oddly massive for their expected origins, formed too early, with no visible stellar ancestry, too big to be from supernova, too small to be supermassive. Some of them fall right into the so-called mass gap, a range of masses where black holes shouldn't naturally exist. Fringe theorists perked up immediately. Maybe, they said with gleaming eyes, those are primordial black holes, and maybe those are dark matter. No one knows for sure yet, but with each new gravitational wave detection, we get a little closer to knowing. Then there's the strange case of dark matter halos. Every galaxy, including our own, is thought to be embedded in an invisible cocoon of dark matter. If two black holes happen to merge inside such a halo, the surrounding dark matter could affect the dynamics of their in-spiral. Not just the final chirp, but the shape of the whole waveform. A little drag here, a little energy loss there, subtle changes, detectable patterns. But only if we know what to look for. There are even proposals that some black holes are surrounded by dark matter spikes, regions of highly concentrated dark matter that form around them like invisible hedgehog armor. When two such spiked black holes merge, their gravitational waveforms might differ from clean, naked mergers. The merger might be messier, longer, more asymmetric. These deviations, if we can spot them, could be our first real clue that we're watching dark matter at work. And that's just one layer. Other speculative models suggest that dark matter isn't just passive, not just sitting there like cosmic bubble wrap, but could actually interact with itself. That could create localized structures, clumps, filaments. These regions might affect how gravitational waves pass through them, not unlike how sound behaves differently in water versus air. We could map those differences. We could begin to image the dark universe, not with light, but with motion. Because gravitational waves are blind to electromagnetic opacity. They don't care if there's gas, dust, plasma, or a mysterious substance that ignores photons. They pass through it all, undisturbed, until they carry that information straight to us. There's even a fringe hypothesis that dark matter could create new types of compact objects, ones that aren't made of normal matter, but are massive and gravitationally active. These could masquerade as black holes but behave differently when merging. Their ringdown would be off, their waveform would end wrong, a tiny deviation, a strange echo. Just enough to make you lean closer and say, "Wait, what was that?" Of course, we're not there yet. These are the dreams of tomorrow's detectors, the kinds of measurements that require precision so ridiculous we might need observatories in lunar orbit or interferometers the size of the solar system. But we're building toward it, with LISA, with the Einstein telescope, with Cosmic Explorer, and maybe even with detectors on the far side of the moon, where the silence is perfect and space-time can hum without interference. Because the longer we listen, the more we might catch the hidden architecture of the cosmos, the scaffolding, the unseen lattice that shapes every galaxy, every star, every breath you take. And gravitational waves? They may be the only messengers brave enough to move through that unseen web and return with answers. So as you finally drift under, breath soft and mind dissolving into that slow cosmic ebb, remember this. There's more to the universe than what shines, more than what burns, more than what screams in light. There's something dark, ancient, quiet, and at last, we've started to hear it. You're far from shore now, deep in the calm where thoughts barely form and time has lost its grip. The stars above are just suggestions. Your body is still, your breath steady, and somewhere on the edge of consciousness a whisper rises. Not from anything near, from the beginning. Tonight we follow the faintest gravitational waves of all. Not from colliding black holes, not from neutron stars, not even from ancient galaxies crashing together in the dark. These waves come from the birth of the universe itself. We're talking about primordial gravitational waves, the holy grail of gravitational wave astronomy. Not made by objects, but by events. Not from stars, but from space-time itself, twisting and writhing in its very first seconds. It's almost too much to grasp, but here's the idea. Roughly 13.8 billion years ago, the universe exploded into being. Not into space, but as space. There was no before. Just an instant of time so dense and so hot that physics, as we know it, broke into shards. And then, inflation. In a fraction of a second, the universe expanded faster than the speed of light. Not matter moving through space, space itself stretching, growing, expanding like a balloon in fast forward. This violent, chaotic expansion likely shook space-time to its core. Imagine ripping a sheet so hard that it sends tremors echoing outward. Those tremors, they were gravitational waves, born before atoms, before light, before anything. We call them primordial gravitational waves, and if we could detect them, they'd give us a direct window into the first trillionth of a trillionth of a trillionth of a second after the Big Bang. Not a metaphor, that's the literal timescale. Historians still argue whether inflation truly happened the way theory describes it. It explains a lot: the smoothness of the universe, the uniformity of the cosmic microwave background, the large-scale structure of galaxies. But it's still unproven. Detecting primordial gravitational waves would be proof. Unlike light, which was trapped for the first 380,000 years after the Big Bang, gravitational waves could escape immediately. They could carry pure information from the moment space-time itself first began to tremble. But there's a catch. You knew there would be. These waves are tiny, smaller than anything LIGO or Virgo could possibly detect. Their frequencies are ultra-low. Their wavelengths are immense, and over billions of years they've been stretched even more by cosmic expansion. So now, they're more like a rumble embedded in the very structure of reality. So how do we find them? One approach is to look for their imprint in the cosmic microwave background, or CMB. That's the leftover radiation from when the universe first became transparent to light. It's been drifting through space ever since, cooling into a faint glow just a few degrees above absolute zero. And if primordial gravitational waves were there at the beginning, they would have polarized the CMB in a special way, creating tiny swirling patterns called B modes. Not to be confused with the ones in your speakers. These are faint curls in the sky's oldest light, visible only in the most sensitive microwave telescopes. Back in 2014, the BICEP 2 experiment in Antarctica thought they had found those patterns. For a few weeks, the physics world lost its collective mind. Then, disappointment. Turns out the signal was mostly interstellar dust. Beautiful dust. But not a Nobel Prize. Since then, experiments like Planck, Polar Bear, Spider and Lightbird have continued the hunt, scanning the sky for that elusive primordial twist in the background light. We haven't found it yet, but we might. And if we do, it would be a revolution. Not just evidence for inflation, but a glimpse into physics at energies we'll never reach in any collider. It would tell us how the universe was born, not from stories, but from data. Meanwhile, other scientists are exploring how direct gravitational wave detectors, like LISA or future ultra-sensitive projects, might eventually pick up these ancient waves. You'd need a detector so quiet, so massive, and so isolated from everything else that it could hear the faint sigh of the Big Bang still echoing through space-time. Some proposals are downright poetic. One plan suggests building a lunar-based interferometer, burying sensors in the moon's crust, shielded from Earth's noise, bathed in eternal silence. Others imagine constellations of space-based detectors in solar orbit, linked across millions of kilometers, all of them chasing one thing, the first gravitational wave. There's even speculation that the primordial waves might contain clues about quantum gravity, string theory, or the multiverse, if such things exist. The way they stretch, their frequency spectrum, their amplitude, all could offer hints about what happened before time made sense. Fringe theorists argue that if the Big Bang was really a bounce, a rebound from a previous universe collapsing, then primordial waves might carry evidence of that former cosmos, like fingerprints left on a doorknob as it closes and reopens. Others suggest that these waves might not be from inflation at all, but from exotic particles decaying in the early universe, or from topological defects, things like cosmic strings, formed in the chaotic phase transitions after the Big Bang snapping and vibrating across space. We don't know yet. That's the most honest answer. But gravitational waves offer our best hope of one day knowing. Because they're not stopped by time, not blurred by matter, not scattered like light. They carry history clean, and if any message from the universe's birth still exists, gravitational waves are the ones holding it. So tonight, as your breath grows shallow and your dreams begin to bloom, let yourself drift backward, not just through your day, not just through memory, but through cosmic time. Picture that first moment, no stars, No space, just energy, just potential. Then, expansion, sudden, relentless. And beneath it all, the universe shuddered, and the shudder became a wave. That wave is still moving. Right now, as you sleep, it may be passing through you. Too faint to feel, too long to measure, but it's there, and maybe someday we'll hear it. The first wave, the first whisper, the first hello from the birth of everything. You've reached the quiet edge now, the furthest shore of consciousness. All the bright noise of daytime thought has faded, and here, there's just stillness. But even in this stillness, the universe keeps talking. Softly, persistently, in waves. So let's ask the question that's been rising beneath every other question we've touched tonight. What is the universe trying to tell us? We've listened to chirps from black hole mergers. We've heard the soft ring of neutron stars collapsing. We've tuned into the hum of the cosmic background, the near-silent tension of pulsars, and the low, long breath of supermassive black holes circling each other across billions of years. We've even imagined the first waves, the ancient shivers from the moment the cosmos blinked into existence. But what do gravitational waves mean? They don't shimmer, they don't glow, they don't form pictures in a telescope or leave streaks on a photographic plate. They are the movement of space itself, the changing distances between things that thought they were still, this silent rearrangement of reality. And that, in itself, is a kind of message. It tells us that the universe is not just a stage, static, unmoving, pristine. It is alive with motion, even in its bones, even in its geometry. It tells us that things we thought were unreachable, like black holes, can leave behind stories. That even if no light escapes, information does, in the form of ripples, patterns, tugs on the ruler that measures everything. It tells us that nothing truly vanishes without a trace. Even the most violent hidden events in the universe send out a final note, and that note reaches us. Not because we deserved it, not because we asked, but because the universe is made to ripple, and we finally learned how to listen. Historians will look back on this era, on the LIGO detections, the kilonova, the background hum of nanograv, and they'll mark it as the moment astronomy changed forever. Not because we saw further, but because we felt more. Fringe thinkers, poets in lab coats, talk about gravitational waves as the heartbeat of the universe. And they're not wrong. Each wave is a beat, a pulse, a confirmation that something out there moved so hard, so fast that it left behind a wrinkle in existence itself. We're learning now to read those wrinkles, to understand what a spin misalignment tells us about how two black holes met, to hear in the waveform whether a star collapsed cleanly or tore itself apart, to track populations of objects we didn't even know existed 10 years ago. And beyond the data, there's something more. Gravitational waves connect us to time. Because they travel unimpeded, they reach us as they were, not distorted by gas clouds, not reddened by dust. They are honest messengers, carriers of truth. They arrive with a timestamp so precise it makes every other method of measurement seem a little jealous. And from those time-stamped ripples, we can build a history of the invisible universe. A record not of what shined, but of what moved. This is a shift in perspective. Traditional astronomy is a bit like photography. We capture the light, the colour, the moment. But gravitational wave astronomy, that's music, it's motion, it's rhythm, it's dance. It's not the portrait of the ballerina mid-pose, it's the sound of her landing on the stage. And so the picture we're building now is a fuller one. We see the light, we feel the motion, we begin to guess at the forces that shaped both. Even better, we can start to predict. When LISA comes online, we'll detect black hole mergers years before they happen. We'll schedule them on calendars. We'll have a front row seat to cosmic events before they unfold. Imagine that. A forecast of space-time just like we do with weather. And maybe, just maybe, we'll find something unexpected. A signal that doesn't match any waveform we've seen before, or a pattern that breaks the math. A frequency from nowhere. Gravitational waves have opened a door, and behind that door is the rest of physics, the unfinished bits. the dark matter, the quantum gravity, the unanswered why. Even if all we ever do is confirm what Einstein told us, that would still be miraculous. Because we're doing it by measuring distances smaller than atoms across arms kilometers long, using lasers, mirrors, and vacuum, while the Earth shakes, and people drive, and squirrels jump. And yet, we do it. We measure the unmeasurable. We listen to the quietest things, and in that quiet we find the truth. So now, as you drift fully into sleep, maybe you won't remember every waveform or every name, but you'll remember the feeling, the vastness, the motion, the weight of the invisible, and the sense that out there, the universe is still ringing, still humming, still telling its story. Wave by wave, and you're part of it now. You always were.